Sometime in the past 30 days, the ground beneath one of America's most beloved national parks quietly rose 6 inches. And the instruments that caught it are now setting off alarm bells in monitoring stations across 3 states. 6 inches doesn't sound like much. We're talking about the length of a dollar bill, less than the height of a coffee mug. But when that 6 inches of vertical displacement occurs across a volcanic caldera system stretching nearly 2,000 square kilometers, when it happens in 30 days rather than 30 years, and when it's accompanied by a cluster of seismic signals that geologists are describing as unlike anything recorded in the past 2 decades, 6 inches becomes one of the most alarming measurements in modern volcanology. This isn't a prediction. This isn't speculation pulled from a fringe website or an anonymous social media post. The uplift data comes from GPS monitoring stations embedded in the ground across Yellowstone National Park, cross-referenced with satellite-based INSAR measurements that can detect millimeter-scale ground deformation from orbit. The numbers are real. The acceleration is real. And the question that every geophysicist tracking this system is now quietly asking each other is the same one you're probably asking right now. What does this mean? That's what we're going to work through today. Methodically, honestly, and with the scientific context this situation actually deserves. Because Yellowstone has a way of generating 2 completely opposite reactions. Either people dismiss it entirely, convinced the threat is overblown, or they spiral into catastrophizing that doesn't serve anyone. The truth, as it usually is, lives somewhere far more complex and far more interesting than either extreme. So let's start with what we actually know. And then let's talk about why what's happening right now is different. Yellowstone isn't just a park. It's a 34 by 45 mile caldera, the collapsed scar left behind by an eruption so violent it reshaped the North American continent, and it sits above one of the most geologically active hotspot systems on the planet. Most people who visit Yellowstone think of geysers, Old Faithful, the prismatic springs with their otherworldly colors, bison wandering across thermal flats like something out of a prehistoric painting. It's beautiful. It's iconic. It draws 4 million visitors a year, but the landscape those visitors are walking across is, in geological terms, the aftermath of a catastrophe. The entire Yellowstone Plateau, the broad, elevated terrain that makes the park feel like an elevated world unto itself, exists because the land above a supervolcanic magma reservoir has been repeatedly pushed upward, fractured, and in some cases catastrophically collapsed over millions of years. The Yellowstone hotspot is a column of anomalously hot mantle material that punches upward through the Earth's crust like a blowtorch held under a sheet of metal. They publish regular updates, weekly monitoring reports, and timely communications when anything significant changes. The University of Utah seismograph stations publishes near real-time earthquake data for the Yellowstone region. These are the authoritative sources. When you see social media posts claiming catastrophe or dismissal, these are the places to check. The ground beneath Yellowstone is moving faster than it has in recent memory. Scientists are watching. The story isn't over yet. There's something else happening beneath the surface of the American West right now. Something connected to the same deep geological forces that drive Yellowstone's unrest, but manifesting in a different form, in a different state, with its own unique threat profile. That's what we're covering next, and if you found this one unsettling, I'll tell you honestly, what's emerging along the Wasatch Front might give you even more to think about. If this kind of deep dive monitoring coverage matters to you, the real data, the honest uncertainty, the genuine science without the sensationalism, subscribing keeps this work going. Drop a comment with what you think is more concerning right now, the Yellowstone deformation, the seismicity, or the hydrothermal changes. Because that question is actually more scientifically interesting than it might seem, and I want to know where your head is at. The ground is moving. We're watching it. And now, so are you. As the North American tectonic plate drifts slowly southwest over this stationary hotspot, it leaves behind a chain of ancient calderas stretching across southern Idaho, a geological breadcrumb trail of past catastrophes. The Snake River Plain, that broad, flat corridor across southern Idaho that you might have driven through without thinking much about it, is essentially a graveyard of ancient supervolcanic eruptions. Yellowstone is simply the current address of that hotspot. The most recent, the most active, the one we're watching right now. Beneath the park, seismic tomography, essentially a geological MRI that uses earthquake waves to image underground structures, has revealed something staggering. There are two distinct magma reservoirs stacked beneath Yellowstone. The shallower one sits roughly 5 to 15 kilometers below the surface and is estimated to contain somewhere between 5 and 15% molten rock suspended within a crystalline matrix, what geologists call a mush zone. Beneath that sits a far larger, deeper reservoir extending into the lower crust and upper mantle, potentially containing enough material to dwarf anything in the shallow system. The University of Utah, which operates much of Yellowstone's seismic network, published research refining these reservoir estimates within the last several years, and the picture that emerged was both more complex and more concerning than earlier models suggested. Now here's what makes the current situation worth paying close attention to. The Yellowstone system doesn't just sit there passively, it breathes, it pulses. Ground deformation, uplift, and subsidence has been measured at Yellowstone for decades, and in that time, researchers have come to understand that a certain amount of ground movement is normal. Expected even. But normal has ranges. Normal has rhythms. And what's been recorded over the past 30 days appears to sit well outside those established patterns. The Norris Geyser Basin, which sits at the northwestern edge of the Caldera and has historically been one of the most thermally and seismically restless areas in the park, has been at the center of this recent activity. This isn't a coincidence. Norris has a documented history of behaving as something of an early warning zone, a place where subsurface pressure changes tend to manifest at the surface before they're detected elsewhere. When Norris gets restless, the scientific community pays attention. And right now, Norris is very restless. To understand why 6 inches in 30 days matters so much, you first need to understand what's actually happening miles beneath your feet, and why geologists don't use words like reactivation lightly. Think of the magma reservoir beneath Yellowstone less like a lake of molten rock and more like a giant sponge saturated with fluid. The solid crystalline framework, the mush, provides structural support, while pockets of actual melt, superheated water, and volcanic gases are distributed throughout. Under normal conditions, this system exists in a kind of dynamic equilibrium. Pressure from below is balanced by the weight and rigidity of the overlying crust. It's not calm, exactly, but it's stable. What drives ground uplift is a disruption to that equilibrium. And there are several mechanisms that could potentially cause what we're currently seeing, each with very different implications. The first, and the one scientists most commonly attribute to Yellowstone's normal uplift cycles, is hydrothermal pressurization. The enormous geothermal system beneath the park circulates vast quantities of superheated water through fractured rock. When heat flux from the magma system increases, or when geological changes alter the plumbing of that hydrothermal network, water and steam can pressurize underground reservoirs, physically pushing the ground surface upward. This is the most benign explanation for what we're seeing. Unsettling, certainly, but not necessarily indicative of anything approaching an eruptive scenario. The second mechanism is more significant. Magma intrusion, the physical movement of molten rock into new fractures and pathways within the crust, can cause dramatic and rapid ground uplift. When magma migrates upward or laterally into the shallow crust, it physically displaces rock, pushing the surface up in measurable ways. The 2014 uplift event at Yellowstone, which researchers from the University of Utah analyzed using GPS and INSAR data, showed patterns consistent with magmatic fluid movement, rather than purely hydrothermal activity. The current event, according to preliminary analyses being discussed within the volcanological community, appears to show similar signatures, and a rate of deformation that has caught researchers off guard. Then there's the third mechanism, and this one is where the term Caldera system reactivation becomes genuinely meaningful. Deep within a magma reservoir, gas exsolution, the process by which dissolved gases like carbon dioxide, sulfur dioxide, and water vapor come out of solution within the melt, essentially like carbonation releasing from a shaken bottle, can rapidly increase internal pressure. As pressure builds, it doesn't just push the ground up, it begins to alter the stress state of the entire system. Faults that were previously locked begin to slip, the hydrothermal system becomes increasingly unstable, and critically, the threshold between the system's current state and a more active eruptive state begins to narrow. The USGS Yellowstone Volcano Observatory monitors SO2 emissions, sulfur dioxide gas released from the volcanic system, as one of its key indicators of magmatic activity. Sulfur dioxide doesn't come from hydrothermal systems alone. Its presence, particularly in increasing quantities, suggests direct degassing from magma. Recent measurements at Yellowstone have shown SO2 flux values that, while not yet at crisis levels, are trending in a direction that warrants careful, continuous monitoring. But here's where it gets more complicated, and honestly, more alarming. The 6-inch uplift figure represents the average across multiple GPS stations, but the deformation isn't uniform. Some stations are recording significantly more uplift than others, which tells geologists something important about the geometry of whatever is causing the surface to rise. When uplift is broadly distributed and roughly even, it tends to suggest a deep, diffuse source, hydrothermal pressurization spreading across a wide area. When uplift is concentrated, forming what geophysicists call an inflation center, it's more consistent with a localized pressure source, either a magma body or a concentrated hydrothermal reservoir, pushing upward from a specific point. The current deformation pattern, based on data being analyzed by researchers at the USGS and the University of Utah, appears to show characteristics of the latter. There may be a concentrated inflation source beneath the northern Caldera rim, and that location, the northern rim, near Norris, is precisely where the system has historically shown the most potential for dynamic behavior. What scientists can't tell us yet, and this is an uncertainty they are explicit about, is exactly what is driving that inflation. Is it hydrothermal fluid migration that happened to concentrate in one area? Is it a shallow magmatic intrusion? Is it the early expression of something deeper in the reservoir system beginning to stir? The monitoring data doesn't yet answer that question definitively. What it does tell us is that something is pushing, and it's pushing harder and faster than the system's recent baseline would predict. Yellowstone has done this before, surged, swelled, and alarmed scientists, and each time, what followed taught researchers something new about just how volatile this system can become. Between 2004 and 2008, Yellowstone experienced one of the most dramatic uplift episodes in its recorded monitoring history. The Yellowstone caldera floor rose at rates approaching 3 inches per year, exceptionally fast by volcanic standards, accumulating more than 7 inches of total uplift over that 4-year period before the trend reversed and the ground began subsiding again. Researchers studying that episode, published in work led by scientists at the University of Utah and the USGS, concluded that the most likely driver was the injection of magmatic fluids, not necessarily fresh magma itself, but super hot, chemically distinct fluids sourced from the magma reservoir into the overlying hydrothermal system. The distinction matters, but so does the similarity. What we're seeing now, in a single month, already approaches a significant fraction of what took 4 years to accumulate during that episode. Go back further, and the record becomes more visceral. In 1959, a magnitude 7.3 earthquake struck near Hebgen Lake, just outside Yellowstone's western boundary. 28 people were killed when a mountainside collapsed into the Madison River, creating a massive landslide dam. The earthquake was so powerful, it caused Yellowstone's geysers to change their eruption patterns. Some went dormant, others that had been inactive for years suddenly reactivated, and Old Faithful's eruption intervals shifted measurably. This wasn't a volcanic eruption. It was a seismic event in a volcanically stressed system, but it demonstrated something that volcanologists still cite today. In a system as interconnected as Yellowstone's, mechanical disruption in one place can trigger dramatic responses across the entire network. Then there's 1985. A swarm, and swarm here is a technical term, not hyperbole, of more than 3,000 earthquakes rattled Yellowstone over a period of roughly 3 months. 3,000 events. The ground shook almost continuously for weeks. Residents in nearby communities felt it. Scientists descended on the park with portable seismometers. The swarm was eventually attributed to movement of hydrothermal fluids through the subsurface, not a precursor to eruption. But the experience underscored just how restless Yellowstone's plumbing truly is, and how difficult it can be in the moment to distinguish between activity that will resolve itself and activity that won't. More recently, in December 2008 and January 2009, a seismic swarm beneath Yellowstone Lake generated more than 500 earthquakes in less than 2 weeks, including a magnitude 3.9 event that was felt across the park. The swarm occurred during a period of accelerating ground deformation, a pattern that some researchers noted bore resemblance to precursory activity observed at other volcanic systems before periods of heightened unrest, though Yellowstone ultimately quieted without further escalation. What history tells us, and this is crucial context for understanding the present, is that Yellowstone is not a static system waiting to explode. It's a dynamic system that regularly cycles through periods of uplift and subsidence, seismic swarms and quiet intervals, hydrothermal surges, and thermal reconfigurations. Most of these episodes resolve without catastrophic outcome, but each one also represents a real, measurable change in the stress state of the system. Each injection of fluid, each episode of ground rise, each swarm of micro-earthquakes is leaving its mark on the rock, altering permeability, adjusting fault orientations, redistributing pressure in ways that accumulate over time. The scientists who've dedicated their careers to Yellowstone are not people prone to alarm without cause. When researchers from institutions like the USGS Volcano Hazards Program, the University of Utah seismograph stations, and the Yellowstone Volcano Observatory speak cautiously about the current episode, their caution is not the same as dismissal. It's the measured language of people who understand that they are watching a system capable of behavior that has no modern human precedent, and who take seriously the responsibility of communicating what they see without either understating or overstating the risk. The current event, they are saying carefully, does not match what came before, not in rate, not quite in pattern, and that distinction is exactly why it's being watched so closely. Right now, the Yellowstone Volcano Observatory, a joint operation between the USGS, the University of Utah, and several federal agencies, is tracking this uplift event in real time, and what they're seeing is raising serious questions about what the next 30 days might look like. The monitoring infrastructure at Yellowstone is genuinely impressive. More than 24 continuous GPS stations are embedded across the park, transmitting ground position data around the clock. A network of broadband seismometers, sensitive enough to detect earthquakes far below the threshold of human perception, feeds data continuously to the University of Utah's seismograph stations, where it's processed, analyzed, and archived. Satellite-based radar systems provide periodic snapshots of ground deformation across the entire caldera, offering a wide-angle view that ground-based GPS can't provide alone. Tilt meters, strain meters, gas sensors, and stream temperature monitors round out a surveillance network that represents decades of investment in understanding this system. What that network is currently showing, beyond the headline uplift number, is a pattern of associated activity that geologists describe as internally consistent, meaning the different data streams are telling a coherent story rather than contradicting each other. Seismic activity in the northern Caldera region has increased measurably over the past several weeks. Not a dramatic swarm, not yet, but a statistically significant uptick in the frequency of micro-earthquakes in the magnitude 1 to 2.5 range, concentrated in a pattern consistent with fluid movement through fractured crust. Simultaneously, ground temperatures at several thermal features in the Norris Geyser Basin have shown anomalous readings, with some measurements running hotter than seasonal baselines by margins that, individually, might be attributed to normal variation, but collectively suggest a genuine increase in heat flux from below. Steamboat Geyser, the world's tallest active geyser, and a feature that sat dormant for decades before suddenly reactivating in 2018, has shown altered eruption behavior in recent weeks. Steamboat's eruption frequency and characteristics have historically been sensitive to subsurface pressure changes, and researchers at the USGS have noted its behavior as one of several surface indicators they're watching in conjunction with the deformation data. The Yellowstone Volcano Observatory currently maintains a color code alert system for aviation purposes and a separate alert level for ground hazards. As of the most recent public communications, Yellowstone remains at aviation color code green and volcano alert level normal. That designation means the monitoring agencies have not yet assessed the current activity as indicative of an elevated eruption threat. It's important to state that clearly and honestly. The official scientific position is one of heightened watchfulness, not alarm. But here's what that designation also means, and what sometimes gets lost in translation. Normal at Yellowstone is not the same as nothing is happening. The alert level reflects the current scientific assessment relative to eruption probability. It does not mean the ground isn't rising. It does not mean the seismic activity isn't anomalous. It means that, in the professional judgment of the scientists monitoring this system, what they're seeing has not yet crossed the threshold that would indicate eruptive activity is imminent or likely in the near term. What volcanologists will tell you, privately and often publicly, is that the gap between normal and the next alert level, advisory, can narrow faster than public communications sometimes convey. At systems like Yellowstone, where the monitoring data can change significantly within days, the interval between a routine status update and a meaningful escalation in alert level can be uncomfortably short. This isn't a criticism of the monitoring agencies. It's simply the nature of watching a geological system that operates on timescales that don't always accommodate human communication cycles. The preparedness picture is worth examining honestly. Yellowstone National Park has evacuation plans. The surrounding communities in Wyoming, Montana, and Idaho have emergency management frameworks in place. FEMA has conducted scenario planning for large-scale volcanic events, including Yellowstone. But the honest assessment from emergency management researchers who've studied the region, including work published through the Natural Hazards Center at the University of Colorado Boulder, is that the logistical challenges of evacuating the greater Yellowstone region in a crisis scenario would be extraordinary. The road infrastructure is limited. The distances to population centers are large, and the populations of communities like Jackson, Wyoming, and Bozeman, Montana, while not enormous individually, represent tens of thousands of people who would need to move quickly through limited corridors. Understanding these gaps isn't meant to generate despair. It's meant to underscore why early awareness matters. The earlier people understand what a potential escalation might require of them, the better positioned they are to respond rationally rather than reactively. Scientists are careful, and rightly so, about speculating on outcomes, but geological modeling exists precisely to help us understand what cascading scenarios might look like if current trends were to continue, and it would be doing this topic a disservice to pretend those models don't exist. Let's be absolutely clear about the language here. What follows is conditional modeling. Scenarios drawn from published scientific literature and geological analysis of what could theoretically unfold under specific circumstances. This is not a prediction. Scientists at the USGS are explicit that they cannot predict volcanic eruptions with precision, and Yellowstone's most recent supereruption occurred approximately 640,000 years ago. The system's recurrence interval, while a subject of ongoing research, does not support any claim that an eruption is due or imminent. These are models. Possibilities. The kind of scenario planning that responsible hazard science requires us to examine. With that framing established, if the current pressurization of the Yellowstone caldera system were to continue accelerating rather than stabilizing, what might the escalating sequence of events look like? The first phase would likely involve continued and intensifying seismic activity. As magmatic fluids or fresh magma push into shallower crust, they fracture rock, and those fractures generate earthquakes. A swarm of thousands of events, potentially including moderate magnitude quakes in the 4 to 5 range, could develop relatively quickly. At Yellowstone, swarm activity of this kind can unfold over days to weeks. Ground deformation would accelerate. GPS stations would show rates of uplift increasing beyond anything in the monitoring record. The hydrothermal system would become violently destabilized. Geysers and hot springs behaving erratically, some going cold as plumbing is disrupted, others becoming dangerously more active. At some point in this escalating sequence, if magma were to reach the shallow crust and interact with the enormous volume of groundwater that saturates the rock beneath Yellowstone, the result could be phreatomagmatic explosions, violent steam-driven blasts that don't require fresh lava at the surface, but can produce significant explosive energy from the rapid vaporization of water. These are not super-eruption scenarios. They are more analogous to what occurred at Yellowstone approximately 13,800 years ago, when a series of hydrothermal explosions created Yellowstone Lake's Mary Bay crater, a feature roughly 2 kilometers in diameter, formed not by magmatic eruption, but by steam-driven blasts. An event of that character, occurring beneath or near infrastructure within the park, could be devastating on a regional scale. Lethal ash and debris over a wide radius, catastrophic damage to park facilities, and the potential triggering of secondary geological hazards. Should pressurization continue beyond that threshold? And again, this is deep conditional territory, the kind of scenario that requires multiple escalating preconditions. The possible idea of a larger eruptive event comes into consideration. Volcanologists modeling Yellowstone eruption scenarios have suggested that even a relatively modest lava flow event, smaller than a super eruption by orders of magnitude, could affect areas well beyond the park boundary. Volcanic ash, even in small quantities, causes respiratory hazards, disrupts aviation, clogs water systems, and, critically, devastates agriculture. The breadbasket regions of the northern Great Plains, which feed a significant portion of North America, lie directly in the prevailing downwind path from Yellowstone. For context on what a super eruption, the one in hundreds of thousands of years scenario, might theoretically involve, published models suggest ashfall across essentially the entire continental United States, with depths that could potentially render large agricultural areas non-functional for years. The global climate signature of such an event would likely include a volcanic winter driven by SO2 injection into the stratosphere. These are not scenarios to dwell on with the expectation that they are imminent. They are scenarios that explain why Yellowstone is classified among the highest threat volcanoes in the USGS's National Volcanic Threat Assessment, and why what happens in those monitoring stations matters to far more than just the communities in Wyoming and Montana. The cascading infrastructure consequences to power grids, transportation networks, water systems, and regional economies would extend well beyond any ashfall zone. Models developed by researchers at Arizona State University and FEMA's hazard assessment teams suggest economic disruption extending across multiple states, even from moderate eruptive scenarios, with recovery timelines measured in years rather than months. None of this needs to happen. The overwhelming probability, based on Yellowstone's documented behavior, is that the current pressurization event will stabilize, the rate of uplift will slow, and the system will return toward its baseline, as it has done many times before. But overwhelming probability and certainty are not the same thing, and in the space between those two concepts lives the entire reason that systems like the Yellowstone Volcano Observatory exist. Here's the truth about Yellowstone that often gets lost between the hysteria and the dismissiveness. Awareness is not the same as panic, and understanding a threat is the first step toward surviving one. What's happening at Yellowstone right now represents something genuinely unusual. 6 inches in 30 days. Concentrated deformation near the northern Caldera rim. Associated seismic uptick. Anomalous thermal readings at Norris. Altered behavior at Steamboat Geyser. Any one of these data points, in isolation, could be explained away as normal variability in a notoriously restless system. The fact that they're occurring simultaneously, trending in the same direction, is what has researchers paying close attention. It may resolve. The ground may slow its rise, the seismicity may quiet, and in 6 months, this event will become another entry in Yellowstone's long database of unrest episodes that came to nothing catastrophic. That is genuinely the most likely outcome, and it's important to hold that alongside everything else we've covered. But if it doesn't resolve, if the trend continues or accelerates, the monitoring agencies watching the system will say so. They will escalate alert levels, they will issue communications, and the communities in the greater Yellowstone region will have decisions to make, potentially on short timescales. What you can do right now isn't complicated. If you live within a few hundred miles of Yellowstone, in Wyoming, southern Montana, Idaho, Utah, or Colorado, it's worth spending an hour familiarizing yourself with your county's emergency management resources. It's worth having a go bag ready. It's worth knowing your evacuation routes. Not because disaster is coming, but because the people who fare best in geological emergencies are almost never the ones who started preparing after the alert was issued. Bookmark the USGS Yellowstone Volcano Observatory website.